The system design round is where message broker knowledge really gets tested. So in this episode, we're going to walk full designs out loud the way you'd actually do it in the room. But before any specific problem, let me give you the template that works every single time. Follow this order and you'll never freeze. Step 1. Clarify the requirements first. Never start drawing immediately. Ask about latency, ordering, throughput, retention, and compliance. Step 2. State your model choice, log or queue, and why. This is the anchor. Step 3. Draw the flow. Step 4. Cover the hard parts, failure handling, ordering, idempotency. And Step 5. Talk capacity and monitoring. Clarify, choose the model, draw, harden, then scale. Let's apply it to a few scenarios. Scenario 1. High-throughput transactional processing, 50,000 operations per second, with exactly once effects and a full audit trail. Clarify. What's the latency budget? Which downstreams? Ordering per entity, retention rules. Model choice? A log, Kafka, high throughput, multiple consumers, and replay for the audit. The flow. The API writes a database row plus an outbox row in one transaction. Change data capture publishes to an events topic keyed by entity. Consumers do validation and enrichment, audit to immutable storage and analytics. Then a single group executor, idempotent with inbox dedupe, performs the effect and emits results. Key decisions. Outbox to avoid dual write, keying by entity for ordering, an idempotency key end-to-end, and Kafka's exactly once for the topic-to-topic hops. Capacity. 50,000 times 1 kilobyte is 50 megabytes per second. Times 3 for replication is 150. About 24 partitions on a few brokers. Monitor lag, dead letter depth, and latency. Scenario 2. Real-time scoring before an action, under 200 milliseconds, at scale. Model choice. A log plus stream processing. You need local state, windowing, and replay for retraining. The flow. Events keyed by entity feed a stream processor running many co-partitioned instances. It does local table joins for profiles and reference data with no database call, windowed velocity counts in local state, and rules plus a machine learning model. Then it emits allow, review, or block. The latency budget lands around 32 milliseconds, well under 200 because everything's local. For model updates, shadow mode, compare, replay 30 days to backtest, then swap the consumer group with zero downtime. And the killer alert. Lag above threshold means you're acting on unscored events, a silent failure. Scenario 3. A stateful entity service with audit, event sourcing plus CQRS. Model choice. A log as the event store with CQRS projections. The right side validates with optimistic concurrency and appends to an events topic, keyed by entity, retained forever with tiered storage. The read side runs independent consumer groups building a key value store for fast current state reads, a relational database for history, a search index, and a snapshot service. Writes are strongly consistent, reads eventually consistent, and you rebuild any projection by resetting its offset and replaying the immutable log. No migrations. Scenario 4. Fan-out notifications across email, push, text, and in-app. Each channel independent and retriable, some low priority. Model choice. Pub-sub fan-out. Kafka or the notification service to queue combo both work. Pick by ecosystem. The flow. A notification event stream feeds one worker per channel, each its own consumer group, so a failure in one channel is isolated from the others. Key decisions. An idempotency key, so a redelivery doesn't double send. Per channel retry with backoff into a dead letter queue. Priority handling, using a priority queue or a separate high priority topic so critical alerts jump ahead. and rate limiting per worker to respect provider quotas. Why not one worker for everything? Because a slow text message gateway must not delay your emails. Separate consumers isolate the blast radius. And one more that's increasingly common. Scenario 5. Migrating a monolith to events. The legacy monolith only writes to its database, and you want event-driven consumers without rewriting it. Model choice. Change data capture into a log. You retrofit a stream onto the database. Debezium reads the database's write-ahead log and publishes table topics, with zero changes to the monolith. New services, a search indexer, analytics, a new microservice, build their own read models off those topics. Later, you graduate to the outbox pattern for intentional domain events, since capturing raw tables leaks the schema. Consumers are idempotent because change data capture is at least once. The talking point that lands. This is the strangler fig approach. New capabilities consume the stream while the monolith stays untouched, and you peel functionality off incrementally. See the through line? Every single one of these started the same way. Clarify. Choose the model and say why. Draw the flow. Harden the failure and ordering an idempotency story. Then talk capacity and monitoring. Internalize that sequence, and system design stops being scary and starts being a checklist. One episode left. The night before rapid fire, to lock it